Welcome back, and today we're going to be talking about a simple but very powerful idea in math, which is the pigeonhole principle. And it is powerful because it can prove some really important things without any complicated formulas. So the basic idea of it is you have pigeons and pigeonholes. And if you try to put more pigeons than there are pigeonholes, every pigeon must go in a hole, then at least one pigeonhole must contain 2 or more pigeons. So looking at it mathematically, if we have n pigeonholes, so let's say we have these lines as holes, so we have 5 pigeonholes. However, we have 6 pigeons, and each of them need to go into a hole. The pigeonhole principle shows us that at least one hole contains at least 2 pigeons. And then there's a more general version where if you place n pigeons into k pigeonholes, then at least one pigeonhole contains at least n over k, where n is our pigeons and k is our pigeonholes, and it's all rounded up. So for example, down here we have 1 over 4 rounded up gives us just 1. What makes this principle so powerful is that it proves something must exist just from counting, even if we never see exactly where it is. So our first question is, suppose you're in a room with 13 people. Can we guarantee at least 2 of them share the same birth month? So the first thing we're going to do here is set up what our pigeons are and what our pigeonholes are. So the pigeons are the amount of things that we have. So in this case, we have 13 people. So that's going to be our pigeons. And then our pigeonholes are going to be where we're trying to group them into. And we can see that we're trying to group them into birth months. So we know that there's 12 months in a year, so our pigeonholes are going to be 12. But since we're placing 13 pigeons, which is larger than the amount of pigeonholes we have, which is 12, the pigeonhole principle guarantees that at least one month has at least 2 people. But by the pigeonhole principle, we can see that we don't know which month it is, and we don't know who is sharing the months, but we know that the shared month must exist. Now for our last question, we have take any 5 points inside or on the boundary of an equilateral triangle whose side length is 1, and we want to show that 2 of these points are always within a distance of 1/2 of each other. So we have an equilateral triangle here, all with side length 1. And we want to take 5 points inside of it, including edges and vertices. And we want to prove at least 2 points are within a distance of 1/2 of each other. So the key idea is to create pigeonholes out of the triangle itself here. So what we can do is put our large triangle into 4 smaller equilateral triangles. So by doing this, we now have small equilateral triangles, all with side length 1/2 for every side. So now what we have is 4 small triangles, and these are what our pigeonholes are going to be. Since they're the 4 regions that we're going to be trying to put our 5 points into. which also shows that our pigeons are going to be equal to 5, since it's the 5 points. But we know that by the pigeonhole principle, if 5 points are placed into 4 regions, at least one of the small regions must contain at least 2 points. So, by the pigeonhole principle, now we know from an equilateral triangle that the maximum distance apart they could be is from one point to another, which we know from before is 1/2. So we know, down here, that the max distance apart is 1/2. But now if you notice, if we place any 2 points, since 2 points have to go into one small triangle, placing any 2 points, even if they're the furthest points apart, is at most 1/2. So because they're at most 1/2 due to the max distance, the 2 points that lie in the same small triangle are at a distance less than or equal to 1/2, which is exactly what we needed to show. And this is exactly what we wanted to show. So if you enjoyed, please let me know what else you'd like to see, and I'll see you in the next one.